Hello, my friends. We're gonna continue studying where we started. 4.2. All right, we're gonna continue 4.2. Let's go. Let's go. Let's go. Let's go. Let's go. NLP techniques. So we took all of these notes, which I will explain them in their video. All right. So we took all of these notes for the past couple of hours. Now we got couple of minutes left, hours left, so let's cover this part. So my technique will be, I'll read it through and alright, so let's go. Linguistics based, or before that, let's try to use Anki notes. So alright, so give me Anki notes 4.2 detailed questions, like certain questions. So let's do certain questions to get to know where the mood is going, the spirit, the ideas, the basics. All right. What the hell? It's generating flashcard. Turing. Elsa failed, by the way. So rule based, yeah. Topic identification, which is identifying text. So supervised and unsupervised, yeah. For supervised, kind of, you know what I mean. Extractive and abstractive. So for extractive, kind of, so you have text and you want to extract the main text, so you get insight from them. When it comes to abstraction, you have the text and you create a new insight, a new summaries from that text, from that summary, from the source. Analogy, like, oh, this is mean. So sentiments differ from topic identification. You know what I mean? Topic identification is more or less is objective, and sentiment analysis is kind of subjective. What do you mean subjective? Is kind of, but there are three challenges. The first one is, sarcasm, and then the negativity, because there can be two negatives. For example, two negatives can be mean cancel each other, or it can be mean, it can be uh, intensifying the negativity. So whoa, that's also the problem. There is also multiple polarity, which means there are positive and negative remarks in one sentence. So you gotta break it down and like chunk them and review both parts as a separate. So that's crazy. So when it comes to named entity recognition, which means you classify entities in your sentence, basically names, age, dates, it can be numbers as well, and data's expression as well. So go. And enmity is what's enmity is machine translation. Old approach with modern one. I don't know which the older was. Oh, yeah, the older was statistical machine translation, which is statistical model to build bilingual text, and also unidirectional for rational. I remember reading that as well. These are the chatbots. Yes. Now let's go. The core concept of rule-based NLP. What are the core concepts? What's the fundamental principle of rule-based NLP techniques? They use set of predefined human crafted rules to tackle the problem around I don't need the outtakes. Cool, 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 cool. Let's go, let's go, let's go, let's go, let's go, let's go, let's go. Timer, I got 1 hour, so gotta read this part at least. Let's go, man. Cool. It's 4 page, so I can finish it. Yeah, I mean, it's 4 page, so I can read it like in 10 minutes. So I can read it like in 10 minutes. So this, so you have time. I can draw it by my letter. I can put it later. I can put it here, but for now I will draw here, and I will just reread it so that I can accomplish my plans. I will not read. I will not type a word. Just I will draw everything. So ancient ones, you know, rule kind of Marusa. So rule means ziga rule hek, you know. Adosha hek rule based. So so you have a split into like individuals, words or sentence words. Okay, yeah, this is very well. The challenge, I think I noticed the challenge as well. What the hell? I think I know the challenge. And called syntactic. Time flies like an arrow, which can be interpreted into many different ways. Time can be So for semantics, we studied three of domains in NLP areas. Application areas are very used. The first one is NLP for machine translation. Very, very important because you gotta understand. You translate speech to and then again to other language. You gotta a little bit semantics is going there right there, and then you have like text semantics because um, um, analysis, semantic analysis. Oh, no, sentiment analysis is very important. Also, because you see, and also text entity, name entity are very, very important tasks. And this discourse is longer than one sentence. So for the first one is topic identification and summary text. Okay, analyzing this course of text involves several subtasks like identifying the topic structure. Okay, now this fourth one is tasks speech. I think speech is used for machine learning. Speech to text speech is cognition. Jesus Christ, what is going on? It is text to speech synthesis. Two tasks. You have here two tasks. For example, you have two tasks. You have here two tasks. You have here like three tasks. But when it comes to syntax, you have two tasks as well. Token and a part of what the hell? Yeah, part of speech tagging. Part of speech tagging. And here we have speech. This is a good summary. Whoa, I finished. I took notes here. All of this is a big notes. So I think this is very good. I can finish this. And I will, well, this is great. Rising. data, machine learning algorithm only, email, algo, alright, text, we convert it into numeric. So there you have figure schema cover. Then you convert it into digits of 1 and the 2. So yeah, that's how you do. So we gotta have some kind of ways, tricks to do this, because in machine learning, algorithms can only take inputs. Therefore, if we wanted to process information from unstructured text, you gotta a way to a computer to process it. So there are two ways. So how to put into vector space? The first one is bag of word. And bag of word approach. So this is kind of more powerful. Neural word. And then the second one is sentence vector. Second one is sentence vector. Alright, now let's begin with bag of word. Okay, bag of words. Right. Alright. Why we say bag? Because once text representation of vector is set into unique bag, all info about text will be discarded. Alright, I don't care what you do. Like Darren loves dog. Darren does not like cats. Cats are not like dogs. So we have three. Darren loves dog. Darren does not like cats. Cats are not like dogs. In the first step, we need to identify all unique words from the text. For this purpose, we use tokenization. Yes, which means Darren and the above the following are used. Darren loves dogs, does not like cats, are. The next step so first step tokenization. For example, let's say this example, Darren loves dog, Darren does not like cats, cats are not like dogs. Okay, Darren loves dogs. First one, Darren. So when we tokenize this, you got Darren. You don't have to repeat it. Then loves and dogs and does not like cats. Cats are there, so are. You don't have to add not and like and dogs. That is it. So you have 1, 2, 3, 4, 5, 6, 7, 8 words. Alright. The resulting will have links 8 links. So it will have 8 words. Now we have 3 sentences and 3 sentences and 8 things. So does the first one exist in the first word? Yes, of course. So we add loves in the second. Yeah, in the first, yes. What about in the second? In the third, do we know loves exist in? No. Does in the third? No. Okay, what about dog? Yes. Second one. No. What about the third? Okay, does. In the first one? The second, yes. Does in the no. What about not in the first one? No, 0. In the second one, not, yes, 1. She in the third one, yes, indeed. Like in the first one, no. In the second one, yes. In the third, yes. Cats in the first one, no. In the second one, yes. In the third, yes. Are in the first one, no. In the second one, no. In the third, yep. So you have this, no. You have this vector. As you can see, I put it here. So how to score? So if the whole example summarized, if the whole example is summarized, what we do is add. So for the Boolean representation, alright. I think count words for the first, for the second one, for the third 2, for the third one, for the fourth 2, and then 2, and the 2, and the 1. Is this count of words resulting reflect how often word occurs? Word occur. We will see it. So what is the limitation? I think I got it. For the first one, I got image. Sparsity. Bro. Okay. More context for since are considered. Neither word order. Yes. 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 Loss of meaning. But the first two, I didn't get this part. Alright. I didn't get this part. Jesus Christ. Syntactic ambiguity. Yeah, I remember this. Yes, yes, yes. This is. Yes, for longer than. I think yes. What is the size of? All right. So, like for example. If you are including very single word in or how small, like sparsity, Yeah, all of them are repetition. I think, yeah. All right. Anyways, we will return back. So let's finish it up. So where the vector? This where the vector? What the hell is going on? Where the vector? Don't write, just draw. So you have two predictions. Skip gram. Let's go, boys. So you have this. Oh man, this is crazy. So it's better to draw and redraw. But first, let's put it here. So to prediction models, continuous and simple graph. What the hell is going on? Mhm. Oh damn! This we can predict the next. Oh damn! If we have one word with a fixed window, like with this model, we can predict Jesus. This is crazy. This is very ah. So yeah. Now you have a sentence, one sentence, and you can put it into a vector, and you have multiple words. Word sentence. It could be discourse or paragraph, and you put them into vector representation. And but the first you can find the length of the word. What is the vocabulary? The vocabulary is a unique characters. Then you can find the sum of the words, actually the vectors existence. I mean, like you have count the word, you can count the word in Boolean representation of the word. Then there are limitations because, for example, you have a word and everything can be zero because like everything is repeated. So you only represent the forefront of the words. So the length can be great, but the vocabulary can be like small. So what is the then like there can be sparse vectors. So yeah, that's and yeah, space will increase kind of stuff. So now you have like word of vectors. Now you got three representation token vectorization method. The first is word to vector TDLF. So this is neural network, by the way, simple neural network. The neural network generates word embedding based on only one hidden layer. A research milestone was passed with the Google researcher published. The model in this, the input layer of neural network expects one hot vector. The one hot vector is bow vector for one single word. Jesus Christ, this is one bow vector. One bow vector, alright? One hot vector is a bow. So let's write this thing. Let's write this thing clearly. Vector, I can finish this for one single word. And this means that all indexes of that vector are set to 0 except for the index of the word which is analyzed. Alright, so this index is set to 1. Okay, and training the neural network for word to vector require a large text corpus. Training the neural network, Jesus Christ, you are my God. Training the neural network is require large, and this could, for instance, be like a Wikipedia dump. When the training is performed, Think again. When the training is performed, a fixed length word window with n length slide over the corpus. The value for n would be, for example, be n equals 5, or like the n is kind of sliding window. So there are two predictions. So the first one is continuous bag of words. Continuous bag of words. This can be used if the goal is to predict one missing word in a fixed window. So continuous bag of words. So you got this, and then this can be used if the goal is to predict one missing word. One missing word in the context of the other n minus 1 words. So as an input vector, you can either use average or sum of. So you can either use average or sum of one hot vectors. All right, and then you got like skip gram. Skip gram if one word within a fixed window. With this model can predict the remaining. So if we have one, like the previous one was if we miss one word, but now if we have one word within a fixed, if we one word within a fixed window, like we can most probably predict n minus 1 context words, the remaining. Yo man, this is crazy. So that's it. Yo man, this is like the word hot vector. So what is hot? One bow vector, one hot like this. Let me write this because this is very, very important. So one hot vector. One hot vector is a POW bag of word vector for one single word, which means you can look it into like this because you have one word here. You check it if that word exists in the first sentence, in the second sentence, in the third sentence. So that is one word. This means that all indexes of the vector are set to 0 except for the index. So you put them all into 0 except for that word, which is analyzed during. Actually, this is crazy. So like let's go. Yo, this is shining outside. So 0, 1, 2, 0, 4, 0, 3, 4, 1, and you put them everything into them. This is neurons in hidden layer. This is actually neuron. Alright, this word vector is neural network. Neural network. I don't know what neural network is about yet. So word of vectors. Right, this as you can see, this is RWO. So actually, from our perspective, I think one missing word area or some of the vectors, and if you know that like this is scheme, if you have one word and you can predict the remaining in -1 is shining outside the word vectors neural networks. So you have like this one word here, but there is kind of the sum of the area or sum of one hot vector. This as you can see here. So one important aspect is the prediction outcome is not influenced by order of the context word. Yeah, nearby are weighted more heavily than more distant context word. Faster, like better suitable for infrequent words. You don't have to remember it. Goal is to maximize for right function will receive from this process is the objective function in NLP tasks. The goal is usually not to find a model. Alright, so I think these are jargons. So, man, what the hell? I should have read this first. I think let's take a break here. Let's take a break. But it is not good to take a break. Let's finish it. Instead, I will draw a picture alone. I'll not write a single word, just to understand it. What the hell? Why should I? I think we're done. We're done, man. We did it. I will review the last parts, the big words, but we spent 5 hours study and we completed. So let's get rest and we will continue tomorrow. I will review this part as well as continue with computer vision part and reinforcement learning. And hopefully by tomorrow I will start 3 and 3 data structure in the dynamics, but before that a recursion as well as. So I don't know which one to choose, but I'll give it like 4 hours, 3 hours session each, and then we can finish. So yeah. This is craziest industry